All right, this is Friday, January 15th, 2021. Physics CP, preparing for final exam next week. And the question came up, how do you do problem 1 from final review sheet, energy and momentum? Now, I haven't printed the problem, but I am going to read it to you now. It says a 10.0 kilogram medicine ball is thrown upwards at a speed of 8 meters per second from an initial height of 12 meters. Calculate part A, the total energy, part B, the maximum height reached, part C, the speed when it hits the ground, and part D, the speed at a height of 7 meters. All right, so I've read the problem and I tried to sketch in real time. This is January 15th, 2021. Not that anyone cares. Physics CP. All right. Now, to do this problem, you could actually cheat and do this problem using the kinematic equations of motion because it's essentially a free fall problem. However, it'd be great if you could demonstrate that you can use energy techniques to answer all 4 parts to this question. So the first question is, what is the total energy of this medicine ball? Energy can exist in the form of gravitational potential energy. It can exist in the form of kinetic energy. It can exist in the form of spring potential energy. It can exist in the form of internal energy, which is the negative of the work done by friction trying to stop objects from moving. In this particular problem, there is no spring, and we assume, so we've got 4 assumptions that we do here. 1, we assume it takes place on Earth. 2, we assume it's a flat Earth. We don't worry about the curvature of the planet if we're doing a projectile calculation. 3, we assume that there's no air resistance, and in this case, that means there won't be any friction, so there won't be any internal energy. And 4, we assume that the acceleration due to gravity is a constant over the height of the problem, so we don't have to worry about how, when you go really far from planet Earth relative to what we're normally used to, that the acceleration due to gravity becomes less and less than just 9.80 meters per second squared. However, if you choose to take my AP Physics C course, we relax each one of those 4 assumptions as you go through the course. And you'll find that you have to actually do an integration using calculus for G varying as a function of R. Yeah. Okay, so anyways, there's no spring, there's no internal energy, and this problem begins with 2 forms of energy. One of them is the gravitational potential energy. And the formula for gravitational potential energy is the mass times gravity, which is the weight of the object, times the height. So really, this is another way of saying the work done is the force of gravity times the distance that it moves vertically. Interesting if you can recognize it that way. And in this problem, we have 10 kilograms. And I know the sheet was printed to just 1 sig fig, but please always do your answers to at least 2. Even 3 is good and won't get you in trouble. But if you round too much, often that will cost you a point. 10 kilograms. In my course, I use 9.80 meters per second squared, so that when we take half of it, it's just a nice, divides evenly by 2. And the height is 12 meters. So that would be 98 times 12. Boop, I get 1,176 joules. And yes, I'll round that off in a bit. In addition, there's kinetic energy, because this medicine ball is moving. And the formula for kinetic energy is 1/2 times mass times velocity squared. So 1/2 times 10 kilograms times 8 meters per second, quantity squared. Beep, beep, beep. So that's 5 times 8 squared, which is an additional 320 joules. When combined with the gravitational potential energy, that will give us ET, and I am the son of ET, that's true. So 320 joules plus 1176 joules, enter, is 1,496 joules. And sure, you can call that 1,500 joules or 1.5 kilojoules. So that is the answer to part A. Part B. What is the maximum height reached by the medicine ball? Well, it starts at 12 meters above the ground, and it's a free fall problem. It goes up, then comes down. To get a calculation for the maximum height, which is this line here, in terms of energy, the energy is being transferred between different forms. It started with a combination of mostly gravitational potential energy plus a bit of kinetic energy. When it stops going up, the kinetic energy will have dropped to zero. But total energy is conserved. It didn't disappear, it was transformed into other forms of energy. And if there's no spring, if there's no friction, then the other forms of energy, there's only one choice, and that is gravitational potential energy. So when it's at its maximum height, the total energy is now all in the form of gravitational potential energy. Therefore, the gravitational potential energy is equal to the total energy, is equal to 1,500 joules. And if you leave it 1496 in your calculator, like I tend to do, that's fine. The formula, of course, is m times g times h. And the h in this calculation will be the maximum height that we're looking for. So h max will be that number divided by 98. And my calculator says 15.26530,612 to 2 sig figs, that would be 15 meters. I'll actually write it out to 3 sig figs. For grading purposes, I like having that third digit available as I check your work, make sure you understand, make sure you're communicating to me that you understand what you're doing. All right, so here's part B. Part C. What is the impact speed as it hits the ground? Once again, we're trying to use energy approaches to figure out the answer. The energy is being transformed. So at the top of its flight, all the energy was in gravitational potential energy. At the bottom of the flight, as it hits the ground, all of the energy is now in the form of kinetic energy. Because at ground height, we're taking ground to be zero height. At ground height, the gravitational potential energy is dropped to zero. There's no spring, there's no air resistance, therefore there's no friction. Therefore, the total energy becomes kinetic energy, which is 1/2 mv squared. Solving for v, I have to take the total energy, multiply it by 2, then divide that by the mass, and finally take the square root of it afterwards. So on my calculator, I go second square root 2 times 1496, because I'm too lazy to round it off, divided by 10, enter. Beep, 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 beep. My calculator says 17.29739,865. So to 3 sig figs, that would be 17.3 meters per second as my answer to part C. Part D. The question becomes, so what is its speed when it's at a height of 7 meters above the ground? And this sketch clearly is not to scale. Really, if I were to do it closer to scale, 12 meters would be more like this much, 6, 12, and then halfway up would be 15. Yeah, that's closer to being to scale. And so forget this. To scale, 7 meters would be around here. It should be going faster than when it was at 12 meters. So it slows down, speeds back up to its starting height, starting speed when it returns to its starting height, and then goes even faster as it heads towards the ground, which we can see here. So we expect an answer to part D to be between the speed of 8 meters per second when it was at 12 meters and a speed of 17 meters per second when it hit the ground. If we get an answer slower than 8 or faster than 17.3, we've made a math mistake. So you should have those thoughts running through your head as you work on these problems. How to do this, though? Well, the total energy in this problem can be divvied up into different forms of energy. But there's no air resistance, no friction, so no internal energy. There's no spring in this problem, so no spring energy. So the total energy in this problem, like the ostrich egg homework we did as we started this unit, it can only be divided between two forms of energy. The energy due to gravitational potential energy, or its height, and the energy due to its motion, its kinetic energy. In part D, they're specifying the height as 7 meters. And so therefore, we can calculate how much gravitational potential energy exists when the medicine ball is at a height of 7 meters. That's going to be 10 times 9.8, which is 98, times 7. I get 686 joules of gravitational potential energy. Where did it come from? It came out of my budget of total energy. So if I take my total energy budget of 1,496 joules and subtract from that the amount of gravitational potential energy that the medicine ball has when it is at a height of 7 meters above the ground, then the remaining energy is how much I have for my kinetic energy. And that value is 810 joules. Finally, finally, I can now solve using the kinetic energy formula, setting it equal to this remaining energy, 810 joules, is equal to 1/2 mv squared. And as before, solving for v, you're taking this 2 times the square root of the kinetic energy divided by m. Before, I wrote total energy only because the total energy was equal to the kinetic energy. To be more proper, I should have written kinetic energy here. Okay, so the square root of 2 times the answer from previous calculation, divide by 10, enter, and it says the velocity at a height of 7 meters. So I'm putting that in parentheses, kind of indicating that's what this means. The velocity at a height, that's supposed to be open parentheses, of 7 meters is 12.72792206, which I'll round to 12.7 meters per second. As I expected, this number is greater than the 8 meters per second when it was 12 meters up, and it's less than the 17.3 meters per second it had when it struck the ground. The next question comes from Final Forces Review, problem number 3. I'll read it. It says the following data was collected from the slider car activity, where there was no friction while it was on the launcher arm. It says the mass of the slider car was 35 grams, the length of the launcher arm was 6.5 centimeters, The distance traveled on the floor was 390 centimeters. The time on the floor was 2.15 seconds. Part A. Oh man. Part A. Calculate the acceleration and the initial velocity on the floor. Great. Part B. Calculate the frictional force between the car and the floor. Part C. Calculate the coefficient of kinetic friction. Part D. Calculate the applied force on the launcher arm. So in every previous year of teaching physics CP, this would be a very straightforward uh, review problem because it comes directly from a lab activity that we would have done in the classroom. This school year, thanks to the pandemic that's killing millions of people, none of my students were able to actually do this group activity. So here's something that you missed out on this school year. Maybe if you take physics C next year, we'll do this activity for you. It goes like this. We give you a toy called a slider car. And a crude sketch of the old slider cars looks like this. Here's a side view of a slider car. And the way it works is it has a little internal hole. The old ones are square in shape. The new replacement ones are cylindrical in shape. And that hole is sized just right so that it fits onto a launcher arm. And the launcher arm is powered by compressed air. So a student in the old days, they actually would take 1 kilogram or 2 kilogram masses and a meter stick and measure the height above the ground that they hold the mass and then drop it so that it applies a consistent force to this compressor here, air compressor. But in recent years, we just told the students, just try to be consistent and repeatable as you do this experiment 3 times. And so what happens is the students bash down on this air pump and that squeezes the air here. This is like, like that. It's not like, oh, I'm stretching the rubber band slowly. It's like, no, almost like you stomp on it. I think they have something called the stomp rocket that is similar to toy. But this one goes horizontal. And so there's 2 parts to this one-dimensional kinematic physics problem. The first part is we assume that while the slider car is still on the launcher arm, that the force being applied is a constant force. Now, in real life, it probably isn't, but we're just taking the average and saying, sure, that is a constant force. And since this mass doesn't change, that would be a constant acceleration. And that's related to part D when they ask, calculate the applied force. Okay, so just talking about the kinematics. Initially, the slider car is at rest. As you stomp on this compressor, it has a constant acceleration, or so we assume, all the way until the slider car reaches the end of the arm. From that moment on, the car now just slides across the floor and eventually ends somewhere halfway or more across the classroom. It still has its little entry hole where the tube had been inserted, that opening in it. But now it's just way over there. And finally, it has stopped. So if you foolishly think of this, you'd say, oh, its initial velocity is 0, its final velocity is 0, so its average velocity is 0. No. This is a two-step physics problem. During the entire time that it was being launched, the acceleration was some large positive constant value. From the moment that it leaves the launcher arm, the air is no longer pushing it, we assume. And so throughout this entire slide across the classroom floor, there's constant friction. If I did a free body diagram while it was here, there'd be the force of gravity, there'd be the normal force, and then there would be friction, of course, trying to stop it from sliding to the right. So friction would be acting to the left. And so this would mean there is a constant negative acceleration until it finally slides to a stop. The boundary conditions between launching and sliding have to be matched. It can't suddenly be going a different speed at the instant it comes off the launcher arm. So, for example, if it was going 1 meter per second at the moment it reaches the end of the launcher arm, then it's going 1 meter per second as it begins to slide to a stop across the classroom floor. So this was an activity that we actually did multiple times in a normal school year. The first time was just to figure out what was the acceleration on the floor, maybe what was the acceleration while it was on the launcher arm. Next time, we added the mass of the slider car and then have you calculate the forces and coefficients of friction. And then when we had time, the new launcher arms could be angled. And back when we taught projectile motion, we would say, okay, launch your launcher arm at 30 degrees and predict where it's going to land. We stopped doing that several years ago now. So, to give you, now that you possibly understand this fun, toy filled activity that you missed out on doing, I'll provide you with the numbers once again. So, the table of information was the mass of the slider car was 35 grams. The length of the launcher arm, this little bit here, only the distance where it's overlapping. The actual launcher arm might be like 9 centimeters, but the part that is inserted into the slider car, that was a length of 6.5 centimeters. The distance that it traveled across the floor after it was launched, so we're not starting from back here, we're starting from the tip of the launcher, was 390 centimeters. And by the way, we measure that from the tip of the slider car when the back end is against the launcher, not shoved in, to the tip of the slider car. Just like in horse races, they measure from the tip of the horse, they measure at the nose of the horse, not the tail end. Okay, so that's 390 centimeters, and the time that it took to slide to a stop was 2.15 seconds. That's all the information you need to totally answer all of this problem. Because you haven't done this lab, I'm not going to call on you students right now at one at a time and ask you, so how do you do part A? Instead, I'm going to use our limited class time today and blitz through this at Mr. Turek's speed. So you can't actually solve part A. I'm going to say part A is when it's on this launcher arm. And the reason you can't solve it is because you need 3 givens, but you only have 2. One given is the distance that it is accelerating over is 6.5 centimeters. The second given is that its initial velocity is 0. But we don't know its final velocity at the end of the launcher arm. We don't know the teeny, tiny fraction of a second amount of time that it spent accelerating. I mean, this is faster than the blink of an eye. It is not 2.15 seconds. You can't measure this with ordinary means. So you can't do this problem. Instead, you have to do the second problem. Even though in time, this takes place after it is launched. For this one, we have three givens. There's our 3-minute bell. I'm going to pause recording and let you contemplate. Resume recording. Okay, so now here we are at the end of the 3-minute break, and I've revealed that you can only solve the second physics problem before you can solve the first physics problem in terms of chronological order. That means in order of time. On the second physics problem, we have three givens. The final velocity is 0. The time that it spent traveling this distance is 2.15 seconds. The distance that it traveled was 390 centimeters. Of course, we should work in units of kilograms for mass and meters for distance. In my head, I know that 390 centimeters is 3.90 meters, and that I can calculate the average velocity as being the distance that it traveled divided by time. So that doesn't help you too much because you're thinking, I need a kinematic equation of motion that I can recognize and understand and use here. And the one to use is the second kinematic equation of motion. Delta x is equal to 1/2, open parentheses, initial velocity plus final velocity, close parentheses, times time. There's only one unknown here, and that is the initial velocity. So if I rearrange this equation and solve for initial velocity, I'm good to go. And before I do too much rearranging, I'm going to remind you that the final velocity is 0. So I'm not going to carry that around too much. Instead, when I solve what's left for initial velocity, I multiply both sides by 2, I divide both sides by t, and that means that the initial velocity as it went across the floor is equal to 2 times the distance it slid across the floor divided by the time that it spent sliding across the floor. Hence, 2 times 3.9 divided by 2.15, enter, is 3.63 meters per second. That is part of part A. In part A, the question was posed, what was the initial velocity of the slider car on the floor? We now have that answer. The initial velocity of the slider car on the floor was 3.63 meters per second, and so that's part of what we're after in part A. But in addition, part A asks, what was the acceleration of the car on the floor? In reality, you could not solve that one until after you got the initial velocity, because none of your kinematic equations of motion excuse me, relate acceleration, final velocity, displacement, and time to each other. You've got one that has initial velocity, displacement, acceleration, and time. In fact, that's the one that we can use right now. But in reality, we can use equation 1 or equation 3 or equation 4 to solve for the acceleration. I'm just going to use equation 1 that says final velocity is equal to initial velocity plus acceleration times time. In this case, the final velocity is 0, and we're solving for the acceleration. So if I say that I take, let's take negative 3.63 meters per second, and then divide that by the time of 2.15 seconds. 3.63 divided by 2.15, and there's a minus sign here. The acceleration was negative 1.69 meters per second squared. So at last, I've answered part A. Now, the initial velocity at the beginning of the floor problem is the final velocity at the end of the launcher arm problem. So, I see. Part B is still talking about the floor because, among other things, we assume there is no friction on the launcher arm, mostly because we have no way of dealing with it if there were friction. So, part B, what is the force of friction? Well, by Newton's second law, F equals ma. And in this situation, when you look at the free body diagram, the net force is caused by the force of friction. So the force of friction is equal to the mass of the slider car times its acceleration while it was on the floor. The mass is 35 grams, which is 0.035 kilograms. Multiply that by negative 1.69 meters per second squared, and the force of friction is negative because it's trying to stop it, 0.0. These are just placeholders. So if I just write 5, that's to just one significant digit, not 3. So you should write it out to 3 sig figs. I have the 5 followed by a 9, followed by a 15, which I'm going to round up to a 2 newtons. Force of friction was negative 0.0592 newtons. Part C. What is the coefficient of kinetic friction? Well, the force of friction is equal to the coefficient of kinetic friction times the normal force. The normal force in this problem is identical to the weight of the car, the force of gravity. So the coefficient of kinetic friction is equal to the force of friction divided by the weight of the car, the weight being calculated by m times g. So if I take the result in my calculator and divide it by open parentheses, 0.035 times 9.8, close parentheses, enter, I have a coefficient of kinetic friction value of 0.172. There are no units. This is a dimensionless result. And that's a testament to how smooth or rough our floor is relative to these plastic slider toys. Part D. What is the applied force on the launcher arm? Now, at last, we're leaving the floor problem and we're dealing with only the launcher arm problem. Now we have 3 givens. We have the displacement is 6.5 centimeters. We have the initial velocity is 0 meters per second. And thanks to the work we did on the floor, we know the final velocity on the launcher arm is identical to the initial velocity on the floor, and that's a value of 3.63 meters per second. So we have our 3 givens. I can now solve for the acceleration on the launcher arm using the fourth kinematic equation of motion. Final velocity squared equals initial velocity squared plus 2 times the acceleration times the displacement. The initial velocity was 0. The displacement in meters is 0.065 meters. So on my calculator, if I type in 3.63 squared divided by 2 divided by 0.065, enter, the acceleration was a whopping 101 meters per second squared. Boom. But they didn't ask. I didn't ask for the acceleration. I asked for the applied force. Well, F equals ma. In this case, m is the mass of the slider car. So multiply this acceleration by 0.035 kilograms, and you have the last answer. The applied force was 3.55 newtons to 3 sig figs. This concludes this particular problem. Okay, A student question came up requesting a little bit more reteaching clarification on part C of this same problem. In part C, the question was, calculate please, what is the coefficient of kinetic friction between the car and the floor? So here's a little reminder. While the car is sliding across the floor, it's moving. It starts off initially, I hope you'll just accept the value that it was moving at 3.63 meters per second. And when it stopped sliding, its final velocity was 0. The distance that it traveled was 390 centimeters, which is 3.90 meters. And this is based on what students really did in my classroom. So they gave it a good thwack, then went halfway across the classroom floor. The part C question was, calculate please, what is the coefficient of kinetic friction in this problem? So this is a combination of kinematic information and Newton's 3 laws of motion. While the slider car was sliding, a free body diagram would show that it had the force of gravity pulling it down towards the center of the earth. This is the weight of the car and is the product of the mass of the slider car times the acceleration due to gravity. The slider car didn't actually fall down to the center of the earth because the floor was pushing upwards on the slider car with a force equal in magnitude and opposite in direction to the force of gravity. That's because it was a horizontal floor. There was a third force. Because the car was sliding to the right, the force of friction between the bottom of the slider car and the floor was acting to try to stop the slider car from sliding. And eventually, it succeeded in bringing it to rest. As you look at the free body diagram, the sum of all these forces is the net force. Two of these three forces cancel. So the net force is just the force of friction that was stopping the car from sliding. The force of friction was the mass of the car times its acceleration. We had worked out previously that the acceleration was negative 1.69 meters per second squared. The mass was given at 35 grams, and therefore we have the force of friction is equal to negative 0.0592 newtons, while the weight of the car is 35 grams times 9.8 meters per second squared. The weight of the car is 0.343 newtons. There's only one equation in the entire known universe that is the fun equation. Fun, I say. Why do I say it's fun? Because that's a mnemonic memory device that says the force of friction is equal to the coefficient of friction times the normal force. The normal force, the N. There you go, fun. In this situation, it's sliding, so we're only dealing with kinetic friction. If it were stationary, we would be talking about static friction. Part C asked us to solve for the coefficient of kinetic friction. Rearranging this fun equation, it says the coefficient of kinetic friction is equal to the magnitude of the force of friction divided by the magnitude of the normal force. Well, in this problem, the normal force is equal in magnitude, just opposite in direction, to the weight of the object. So the numbers I'm going to plug into this equation are 0.5 I didn't write that, did I? 0.0592 newtons as the magnitude of the force of friction. And in the denominator, 0.343 newtons as the magnitude of the normal force. The coefficients of friction can never be negative. They are dimensionless. The units cancel. The value of 0 would mean that there's no friction. The greater the value, the greater the roughness between these surfaces. So on my calculator, when I type in 0.0592 and I divide that by 0.393, enter, there's my result, which you can't quite see. It says, oh yeah, the coefficient of kinetic friction in this problem is 0.173. A question has come up on Forces Review questions 6 through 8. I'm not displaying the questions, but I'm going to read to you what I'm seeing as I look at the sheet. It says, use the following data table to answer questions 6 through 8. On the data table, it says the first column is object, and it lists the Sun, Mercury, Venus, Earth, and Mars. The second column is the distance from the Sun in meters. The third column is the radius in meters. The fourth column is the mass in kilograms. Number 6, calculate the gravitational force between the Sun and Part A, Mars, and Part B, Mercury. Number 7, the space shuttle, 15,000 kilograms, is located 2 times 10 to the 5th meters above the surface of the Earth. Calculate the gravitational force between the shuttle and the Earth. And question 8, the one that the student just asked me to solve. Calculate the acceleration due to gravity on Venus. If the average mass of an adult is 65 kilograms, what is the weight of an average adult on Venus? These are physics problems that we would normally have taught you how to solve during the regular school year. Unfortunately, this year, you didn't learn this material. So I'm going to answer the question, but do recognize that this is material that we didn't have time to do. By necessity, I'm going to have to give you the extremely short story version of this. So once upon a time, Isaac Newton was waiting to get into college. He was on his family's estate, hanging out in the apple orchard. An apple fell. He wondered, why did the apple fall? The moon happened to be up in the sky, and he wondered, is it the same force that makes the apple fall that makes the moon go round and round the earth? He worked out that it does, and eventually published what is called Newton's law of universal gravitation. It says the force of gravitational attraction between any two objects in the universe is the product of a constant called the universal gravitational constant times the mass of the first object times the mass of the second object divided by the distance from one object to the second squared. Of course, from the center of one object to the center of the other. Now, as you see this equation, which you're probably seeing for the first time, it should seem oddly familiar to you because Coulomb's law looks very much like it. Coulomb's law says the force of electrical attraction or repulsion between any two charged objects is the product of Boltzmann's constant, lowercase k, times charge q1 times charge q2 divided by the distance from the center of one charge to the center of the second charge squared. That's right. They are very similar to each other. One just deals with electric forces, the second one deals with gravitational forces, and physicists have been working for decades to find the grand unified theory, the guts, they call it, the grand unified theory that connects all four known forces in the universe together into one granddaddy equation. Okay, they've made progress, but to answer number 8, let's just focus on this part. As you stand on the surface of a planet, the distance from the center of you to the center of the planet is essentially just the radius of the planet. In the case of Venus on the table, the value listed for Venus was a radius of 6.05 times 10 to the sixth power meters. And by the way, Earth is listed there. You can see that that Venus is about 80% the size of the Earth. So it's our sister planet for that reason. The mass of Venus is listed as 4.87 times 10 to the 24th power kilograms. What is not listed is the value of the universal gravitational constant. And without that, you can't do this problem. Before I do that, I want to say the distance from the center of you to the center of the Earth, you might say, oh, I'm 2 meters high. Okay, so the middle of you is 1 meter up from the center of the Earth. If you add 1 meter to 6,050,000 meters, that's insignificant. And your mass is going into this equation. All right, anyways, the universal gravitational constant that you would need to solve this problem has a value of 6.672 times 10 to the negative 11th power newtons meter squared per kilogram squared. Doing problem 8. Calculate the acceleration due to gravity on Venus. Here's the neat trick. You guys know that on Earth, if this were the Earth, your weight would be m times little g. But this equation is what's really taking place. It's really capital G times the mass of the Earth times your mass divided by the radius of the Earth squared. These are identical here on the surface of the Earth, which means the acceleration due to gravity for any planet is the product of the universal gravitational constant times the mass of the planet divided by the radius of the planet squared. So that's how we get the value of G on Venus. I'm not going to bother writing it out because I'm going to save time. I'm going to go 6.672 times 10 to the negative 11th times 4.87 times 10 to the 24th power divided by 6.05 times 10 to the 6th power x squared, enter. And my calculator shows the acceleration due to gravity on the surface of Venus is 8.88 meters per second squared. So you're a little lighter on Venus than you are on Earth. On Earth, it's 9.80 meters per second squared. On Venus, a little bit less. So how do you calculate the weight of a 65 kilogram person? Your weight is equal to 65 kilograms times the acceleration due to gravity on Venus. So if I multiply this number by 65, the answer is there, 577 newtons. Of course, down towards the center of the planet. A student posed the question, how do you do forces final review question number 1? Sadly, this is yet another example of the disadvantage you students have this school year by not being in our physical classroom. I think I'm also going to gripe about, gee, I'm so scared that risk management didn't want me to do any activities with you. This is clearly an activity you could have done at home. Number 1 reads, using a spring scale, you hang a metal block. the scale reads 22.5 newtons. What is the mass in kilograms of the block? So I'm going to do a quick sketch. Here's the ceiling. Here is a spring, and it's normally housed in a little plastic rectangular thing. So that's a spring scale. And from the spring scale, I'm hanging a metal block. When I hang it, that causes the spring scale to stretch. And there's a little pointer on the spring scale, and it's calibrated using Hooke's law. F equals kx is Hooke's law. The force of the spring is a restoring force. So as I stretch this thing downwards, the force is pulling it back upwards, and it's linear. So if I double the distance, it doubles the force. Great. So in problem number 1, you're hanging this mass on the spring scale. Really, you're holding it in your hand, but that's equivalent to bolting it to the ceiling. And the scale reads 22.5 newtons. And the question is, so what is the mass of the block? In this situation, what you're supposed to recognize is, if you do the free body diagram, it's the weight of the block that is stretching the spring scale. And the spring scale stretches further and further and further until the upward pull of the spring scale cancels the weight of the hanging metal block. So when the spring scale reads 22.5 newtons, that means the weight is 22.5 newtons. And if you know that the weight is 22.5 newtons, you assume it takes place on planet Earth, you can now rearrange the equation to solve for mass. 22.5 divided by 9.8. Enter. The answer is 2.295918367, which I would round off to 2.30 kilograms. That 3 is significant because we're rounding up 2.2959. So it's 2.30 to 3 sig figs. To 4 sig figs, this would be 2.996. Okay, so it rounds up 3 sig figs. The period has ended. I finally printed off a copy of the Forces Final Review sheet that everyone is asking about. And I have a student who is right at the end of the period was asking me to go over problem 2. So I feel the best thing to do really is to end this particular recording, because it's already 53 minutes long, and just start a new recording of the answers for this document.